Welcome everyone to the Wisconsin Robotics Seminar Series. As a reminder, our seminar series has speakers in robotics, human-robot interaction, human-robot collaboration on the first Wednesday of every month at 1 p.m. Central Time. This is the last talk of the fall 2022 semester. We're going to hear a talk for about 45 minutes, and we'll have a 15-minute Q&A at the end. If there are any questions during the talk, please ask them in the chat. If it seems like it's a timely question, I'll bring it up, and the speaker can also decide on answering them, but I'll collect most of the questions to ask at the end. So to introduce today's speakers, it's Professor Boyi from the Department of Industrial and Systems Engineering from the University of Florida. Dr. Hu got his PhD from the West Virginia University in ergonomics in 2016, and he worked as a postdoc at the Harvard T.H. Chan School of Public Health. And he's been working in the areas of human-robot interaction, human safety systems, human motion prediction. And today we're going to be hearing about ergonomics of robotic-assisted remanufacturing. Without further ado, I present Dr. Hu.
Thanks very much for introduction. Good afternoon, everyone. Thanks for having me. I will appreciate that. I will be giving a talk and share some of my ongoing projects. So the title is Ergonomics in Robotic Assisted Remanufacturing. So let's go and get started. To start, I would like to show the disclosure to the presenting the work. So the primary work is supported by NSF, and as we also have a small portion as the workforce training, which is funded by NIST, and actually the preliminary work part of this work was funded by NASH, and some of the algorithms we are developing and we have developed from this project, we are working on transferring to a project that is supported by a Department of Transportation. Okay, so next, a little bit about myself. So about my background and how I start and accumulate my interest in HRI, human-robot interaction. So as I started my PhD, I got my PhD in ergonomics from West Virginia University in Morgantown, West Virginia. So you may know that there is a NIOSH center, okay, in Morgantown. So that's the where I got to know the robotic safety, and I visited that center multiple times during my PhD program. And after that, I got the opportunity to work as a research fellow at Liberty Mutual Research Institute for Safety. At the same time, Harvard Research, T.H. Chan School of Public Health. This is the parallel experience. I work on two projects same time for 2 years, and during the 2 years, I accumulated further experience using emerging technology, wearable sensors, 3D lidars, and mobile robots on safety-related research projects. And then I started my position at UF, and I gradually, work on different sorts of HRI problems, both in manipulator as emulators. Okay, so for talk today, I would like to share one important aspect of my research, which is the remanufacturing and end-of-life electrical and electronic waste recycle. Okay, so I will introduce the motivation and a little bit of the background, and then I will introduce 3 of ongoing projects. Okay, and then I also would like to discuss some of the future works and acknowledgements. So in terms of the motivation, and nowadays, customers, different stakeholders, we are having a more and more interest in this in this problem. Okay, so through manufacturing and end-of-life products recycle receive more attention. First, from the environmental regulation perspective, some of the, especially the electronic waste, they have the potential of polluting the environment. right? Some of the products include heavy metal, gold, silver, copper, lead, etc. And then consumers, we are more and more interested in green products, right? All sorts of green products, electronic products. Based on a recent report, Apple claimed that 20% of its products were manufactured using recycled elements, and another example would be in e-vehicles, right? Customers, they are just getting more and more interested in those type of stuff. And next is due to the scarcity of resources, right? Some of the resources, humans are just almost depleted, all of them, especially some of the heavy metal for making the chips and making the camera, etc. The list go on and on. And more importantly, there is the potential profitability of salvaging operations, okay, as the for-profit institutions, they can see a huge potential making a profit by doing. And next is when we consider the problem from both the input and output ends, we can see, globally speaking, the electronic waste production reached a record of 53.6 million tons in 2019, increasing almost 20% in just 5 years. I would say European unions, they have a better organized data system than the United States, but the trend is very consistent. Simply because right now we are just making more and more those type of electronic products, and recycling is still a challenge problem. Next is a price reduction of up to 50% for marine manufacturing parts compared to new parts is possible in industrial examples. Okay, not only in terms of electronic products, but as well as other machines, mechanical machines, or similar products. And this concept is well accepted by the industry. Okay, this is another strong motivation. And another motivation is, as a matter of fact, Asian and African countries are the final destination for recycling and disposal of approximately 75% to 80% of the global e-waste, historically speaking, mainly through the just a few in the landfill or whatever methods. But the previous practice of exporting e-waste have been disrupted since mainly in the China effectively banned e-waste imports in 2018, followed by many other countries. So in other words, right now, as a nation, United States needs to deal with this type of waste domestically. We need to find a solution. Okay. And today, e-waste disassembly is still a labor-intensive process that poses significant occupational hazards to human workers, both in terms of occupational injury as well as occupational disease. Okay, so the pollution, toxic materials, musculoskeletal disorder strains, coalition, you name it. And another problem, if you want to propose fully automation to replace human workers' input, is, compared to manufacturing processes. Okay, remanufacturing is not a simply reverse process, because the status of end-of-life electronic products vary significantly. There are a wider range of manufacturers and models, right? It's impossible to develop a system that handles all sorts of end-of-life products. Okay, so in other words, in my opinion, there are still at least two technical challenges, fundamental breakthroughs needs to be made. The first one is the identification, system identification, because we have so many different makes and models of the end-of-life products, is beyond the current capability of the AI system to recognize those systems and which parts are valuable to recycle. The second is the planning. Okay, so for this disassembly of the end-of-life electronic waste, so it still needs human input to decide which parts and the sequence of dismantle. So the proposed work, the large project, effort target the disassembly line for remanufacturing towards efficiency, safety, and sustainability. So the robot manipulators and the human workers will collaborate among each other for the disassembly, repair, and replace tasks in remanufacturing factories. Okay, this is a demonstration, this figure. Historically speaking, before the concept of remanufacturing and end-of-life product recycle is the economy model is pretty linear, right? Is the if you like, is the from crib to grave, right? But right now, more people are welcoming a recycle, a circular economy model, right? It is from the okay, we will try to recycle and reuse as much as the components as possible. And since the problem is so complex that beyond the current capability of the AI agents, we still need to rely on the strengths of both sides of both humans and collective robots. And this is the overall structure of the project. So this is the project has 5 PIs. So we have a PI from mechanical engineering domain, robotics control. Okay, so they have learning expert. For me, today I will only introduce the project that I lead. So mainly the task number 3, the work-centered human-robot partnership design, and task number 5, human-robot partnership informed process planning, and part of the part 4. Okay. So let's start with the first study, is the sequence planning and the task allocation. So the objective for this part is to find the optimal disassembly sequence and allocate tasks between humans and robots based on their particular strengths and physical capabilities. So the key methods we use in this project is first task modeling as human factor and ergonomics. Researchers will use hierarchical task analysis. And next, I will introduce some of the variables we decided to include in our optimization model. And then I will introduce the optimization model we developed. Okay, so as the use case, we decide to select the a desktop disassembly task. We deliberately choose these mid-sized electronic product, now to make it as representative as possible. So we didn't use disassembly of a cell phone or a pad. It's too small, or we didn't choose other very large, display, TV, printer, those type of large electronic products as well. So we believe if we only can choose one, the desktop is the best use case. Okay, so for this desktop is the dial, there are some moderate differences among different manufacturers and models, I would say, but overall speaking, those are the essential measures that have to be handled, okay, during pretty much all electronic waste recycling tasks. Okay, I will introduce those measures in our next slide. Okay, through the hierarchical task analysis, we decide, we analyze the product modules, and we identify those five big modules we need to remove. Okay, first is we would like to remove the hard drive due to the privacy concerns. Nowadays, we work with the industry partners, we work with the over campus, university surplus teams, and currently, no matter what route you go through, the product goes through, they need to manually destroy and remove the hard drive for privacy concerns. Okay, this is for this product. In order to remove the hard drive, we first need to remove the optical drive, and there are certain subtasks. And next is we need to remove the heatsink in order to remove the chips of the computer. And the third one is we would like to recycle the RAM. And this is one of the most straightforward products measures that can be recycled and make a profit. Okay, sorry. So through the hierarchical task analysis, we identify we analyze the whole sequence and identify these are the subtasks as listed here. Next, we used string index SI, which is a well-known tool to evaluate the risk of developing musculoskeletal disorders in distal upper extremities, including hands, wrist, forearm, and elbow. So we made a decision because we believe for these mean-size electronic product manipulation, this is the appropriate method. Okay, maybe in the future for large printer or display, TV, wash machine, that type of thing, disassembly, which involve a higher muscle output in terms of for the lower extremity or lower back region, we may use other methods. But for this one, which involves a lot of hands or upper extremity subtle manipulation, we believe string index is a good one. Okay, string index is measured by reading 6 parameters on scale of 1 to 5, which include intensity of exertion, duration of exertion, efforts per minute, hand raise posture, speed of work, and duration per day. Okay. And we have assigned numerical values to each of these factors, and then we multiply them together and get a string index. Okay, this is a part of the story. Next is we also select and decide to use another factor which we believe is important in this process, which is the ability for the assembly of that module. This factor we obtained from previous literature, and this factor describes the level of complexity of the disassembly task. And for the DS factor, it includes 8 parameters, which includes the size of component and the weight of component, the tools required for removing the component, manipulating the component, and accessibility of that module during the operation, and the component shape and operation complexity, positioning, which means whether it involves a very precise positioning operation, and operation force. Okay, so each factor parameter has 3 levels and has a numerical value assigned to it, and through a summation, we got the disassemblability score. And so these slide shows after the THA analysis, there were 17 work elements. Okay, and these highlights the SI and DI score, and this is a description of the work elements. And next is the optimization model development. Okay, so this model was developed by another PI on the team. Okay, I'll just save time. In short, this optimization model, this problem, we try to maximum the reward, and we consider so the completion time of the operation. We will try to consider include the string index and the disassembly score and in the model. Okay, and this is the result part. So for each one of the overall utility, based on the overall utility, we decide and identify a cutoff value, to assign that specific task to either a human or the manipulator. Okay, in order to achieve the highest optimum overall utility. And for this specific case, so these are the two optimal operations. It doesn't matter if we go back. Okay, it doesn't matter if we first remove the module A or module B. It induced the same utility in the end. Okay, and to sum, the work has been published in Journal of Mechanical Design earlier this year. And in terms of future work, we will definitely like to work on more models and make the products and we will also try different factors. For larger products, we would like to include other assessment tools other than string index, and also we like to run, most importantly, we would like to run some systematic assessment, human in the loop, human subject experiment to verify whether the circuit planning is really can induce the optimal consequences. Okay, so that is the second part of my talk is the ergonomic evaluation. The objective is to quantitatively evaluate the effects of working with a collaborative robot during the e-waste disassembly process on human workload and ergonomics through a human in the loop experiment. We would like to objectively assess what sequence will introduce the optimal outcomes. So for today, I include sample size of 10. Actually, we collect a much larger sample size, but this is an ongoing project. My PhD student, this is actually the primary part of his dissertation. Currently, up until now, we only process 10 subjects. So that is the most we can share today. Okay. And instrumentation. So we use the IMU-based motion capture system to track the participants' full body kinematics performance. And we use Robotics UR5 in the experiment. We also include eye tracking, EMG, and heart rate variability matters. But as I mentioned, students are still working on processing the data. So today I can only share the IMU part of the results and some of the subjective questionnaire. Okay, the independent variable is the working mode, and it has two levels: performing the disassembly task manually or with the cobot assistance. And the dependent variable, we include the NASA TLX, and we include the worker's movement pattern, joint made by a robot. And I don't think I have time to play the video, okay, but I can give a verbal description. So as you can see, the is pretty much a sequential operation, which we'll be discussing later. Okay, so you can expect there will be a lot idle times while the robot is working on something the human worker needs to wait. Okay, and next, okay, here comes the results. I can only share some of the preliminary results, but the overall looks promising. First, in terms of NASA TLX, until we only process the sum scores. Okay, so with the introduction of the manipulator, collector robots, the overall scores dropped significantly from 165 to a little bit less than 100, and it is very significant. Shows overall speaking, the workload has been reduced successfully, and we also process some part of the kinematics. So sagittal L5S1 flexion angle with the robot, we observe a neutral posture, as you can see, because the human worker didn't need to use very awkward and extreme postures. He or she didn't need to move and carry the case, the hover around. Okay, which is also a positive sign. And I list the mean shoulder flexion, both sides, but the bilateral side of the shoulder flexion angle, but abduction and rotation also shows a more neutral. Okay, which means less stress. It could be less stress on the shoulder and upper extremity. Okay, all these are positive signs. Well, it was noting that task completion time, on the other hand, has been increased from 105 seconds to 159 seconds using the Clever robots, which is not surprising, I would say, because the cobot cannot move with high speed and power, and as I mentioned, the task allocation, the overall task was pretty much sequential, and the task completion time was the increase was expected and can be solved through other methods, which will be discussed later. And the conclusion is this is ongoing analysis. Hopefully, in about 2 to 3 months, my student can finish the majority of that analysis. He can add the eye tracking data to objectively assess the human workload, the cognitive workload, and also he can add the EMG sensor data and heart rate variability data. But until now, the results from the study reveal that compared to the working alone condition, working with the cobot reduced the overall human workload and the physical stress that the disassembly task placed on participants. However, the task completion time was found to be negatively impacted when working with the cobot, and indicating there is a trade-off, okay, and that needs to be taken care of. And in terms of the future work, and we would like to do, add more analysis and not only focus on the upper extremity, but also the full body kinematics analysis. Not only in terms of their posture and behavior, but also the risk of falling, the balance maintenance, etc. And more importantly, we would like to seek their collaboration mode. Okay, so currently we only have one human and one robot, and that's the primary reason we had a lot of idle time. We'd like to see if we can, and also this part is connects back to the study number 1. We'd like to see maybe a more complex and another dimension of the optimization, through better design and allocation if we can add, say 2 human workers with team up with 1 collaborator to partially solve the problem. And the final task project we're working on is related with artificial intelligence and machine learning. As we can see during this HRC task, real-time human task recognition is essential to ensure a smooth collaboration between humans and robots. But it still remains a significant challenge. Okay, up until now we have, there are lots of different solutions being proposed. Okay, image-based, RGBD-based, point cloud-based, and variable-based. Actually, no method is perfect. Each has its pros and cons. And for this specific electronic waste recycling and remanufacturing, one of the problems is the lack of appropriate data sets for lack of data sets for the initial model training. Okay, because currently the public accessible data sets mostly include some of the domestic living activities. They do not have a high resolution and representative of the occupational tasks that we are dealing with right now. And in order to be a viable solution, also algorithms need to be work in real time with satisfactory performance. Okay, so as a team, different PIs, we try to tackle this problem from different perspective. We have a computer vision expert on team, but for me, since I've been working with wearable MU-based motion active recognition analysis for some time, so that is how I try to solve the problem. Try to develop MU-based deep learning models for task recognition, allows robot assistants to detect human motion intention during disassembly processes. And specifically for this task, we combine experimental data collected with the collection with deep learning. We include 3 specific deep learning models. One is the pretty classic convolutional neural network, and we include LSTM, long short-term memory network, and the third one is the GoogleNet for the accurate assembly task recognition. And moreover, we developed a small add-on module, a sequence-based correction module, to further improve the accuracy of the overall pipeline. Okay, and this shows the overall system workflow. Okay, for this specific experiment, we included 22 participants, all from university student population, and we used desktop disassembly has been selected for the study. And we use 6 MU sensors while performing the disassembly task. And the sensors were placed on the both sides of hands, forearms, and upper arms to track their upper extremity movement. And there are 6 tasks, sequential tasks during this disassembly. Okay, which are first remove the thumb screws, second remove the cover of the desktop, and remove the hard disk drive, remove the fan, remove the heatsink, and remove the memory module. And each participant need to repeat 5 times. And in terms of data processing, over 570,000 frames of motion data were collected. And for joint angles, okay, I think I need to speed up. I think next slide. This slide shows the basic structure of the model. And for in terms of input, we include both the joint angle and the second positions from the 6 sensors. Okay, and the input is we used 4 data points from the time series. Okay, and later on I'll explain why we select 4. And in terms of output, the different machine learning models, they predict which task the participant is working on. 6 tasks. And the first one is the CNN model, and this is the structure of the CNN model. Okay, it's a pretty standard deep learning model, neural network. And next is the LSTM model, and we tried 5 different hidden sizes of LTM, 16, 30, 32, 64, up until 512. And later on, I'll explain, the results, the compare results. The learning rate was set at 0.01, and we used them as the optimizer, and decay rate was set at 0.1 for every 6 epochs, and the Croft entropy loss function was applied. And the third structure we used was the GoogleNet. GoogleNet is the widely accepted model developed by Google, and there are 22 layers in this structure, which was trained by 1 million images with 1,000 types of objects. And in this study, we had to use the transfer learning because technically the data of input was time series data, and we need to use the transfer learning module to utilize GoogleNet as a pre-trained parameters. And the learning rate was 0.001 with a momentum of 0.9, and SGD optimizer, the decay rate was 0.1 for every 7 epochs. And next is the sequence-based correction algorithm, that module we developed. Okay, I think I need to skip the detail. I'll show you in the result section what this module does primarily. And model training. So we used 66 trials for training, 22 for validation, and 22 for testing. And this is the spec of the machine that we use to train to run the model. And here comes the results. Okay, so first this profile, the curve shows the overall accuracy when using different lengths of the window as the inputs. And as we can see, the 4 points for each time series induce the highest accuracy, 88%. So that's the reason why I decided to use input size of 4. And this is the computer matrix of the CNN model. Second is the LSTM model, and we compare the hidden size of 5 or 6 different hidden sizes, and technically speaking, the top 3 they don't make a difference. Okay, so from 128 to 512, their accuracy is all the same, 91%. And third one is the GoogleNet, and GoogleNet has the highest accuracy, 92%. And if we add the sequence correction module, okay, we had the highest accuracy, which 5%. Overall speaking, this is we merge this module will merge the prediction to the central, right? So is impossible for the predictor, the algorithm, to predict a far way off prediction. And here's the result in terms of testing, accuracy, and time, and the delay. So the GoogleNet with it has the highest, most complex structure, which induce the highest delay, but we believe 5 milliseconds delay is totally acceptable, and that to be used in real time, if we will. And in terms of future work, we would like to see, instead of merely relying on MU or image data, hibernate, okay, a model using data fusion may improve both the accuracy and the robustness of task recognition during the disassembly process, because each method has its pros and cons. And we would like really developed the online machine learning module for task recognition in real time. And this is another part of my PhD student dissertation. Okay, and we would like to conduct a human participant experiment to evaluate and assess the usability of this module performance. And finally, here's the acknowledgement. Just mentioned, this is the team lineup. We have 5 PIs, and the majority of the project was made possible by National Science Foundation. And this is the final slide. Is my personal contact information. This is the QR code for my web and my lab. If you have any questions, feel free to contact me anytime. Thank you.
Great. Thank you, Boyi, for the great talk. So Mike and I have been writing down questions that we want to ask, but
Sure.
while we ask them, we'd like to invite anyone listening to also please ask questions using the Q&A feature. Just post them and then I'll position it. So some basic questions, Boyi. Sure. You talked about remanufacturing, disassembly.
Mm-hmm.
What are other aspects of remanufacturing in addition to disassembly that there exists? Like, so is disassembly the biggest target right now, or is there more steps to be done after that?
More steps being done. So I have okay. I think disassembly is one part. Okay, remanufacturing has cleaning, troubleshooting, analyze, sorting, and identification. So disassembly is the part we're working on, but in terms of scaling up and converting what we have in other aspects. So this is on our to-do list.
Got it. Yeah, I think I was enamored by the robot. I ignored that graphic on the left and I was just looking at the robot. Okay, this is very helpful. So if a product is, for example, being refurbished, you would still go through these processes. It could go to recycling, refurbishing, and things like that.
Exactly. Yeah, but this may need some decision analyzed to decide what is the best route for a specific product.
Yeah, got it. There's another question that I had, and I'm seeing that Rob Radman asked the same question, which is in study 2, the results depend on the allocation, right? So,
yes.
You know, if you increase parallel work, you would shorten the time it would take, but you might lose out on the other features, maybe the task load features and stuff like that.
Exactly.
Rob is also asking the same question. He's curious about how you could try to increase cycle time, by adding more robots maybe, or maybe increasing parallel work. Can you talk about those options a little bit more?
Sure. Yes. Okay, I think here's maybe this part. So options number 1 is this is ongoing analysis, and we only present one part of the experiment. As maybe you and Rob have identified, these results, the human performance, ergonomics performance, is heavily impacted by the task allocation, right? The task allocation. One of the main purpose, objective of this part is if we vary our optimization model. So if we have different task allocation, we want to compare using a human experiment to see whether the results are in line with the model prediction. So this is the first objective. But to answer your question, if for a specific task allocation, or we are trying to see different options by adding another manipulator. So 2 manipulators serve 1 worker, or we're trying a human workers works on 2 products disassembly at the same time and parallelly, while the robot and the human collaborate on the same task. So that, quantitatively speaking, it can also reduce the idle time significantly. But this part also needs to go through ergonomic assessment.
So to build on that, I think part of Rob's question is, you know, if you add multiple robots, you can increase cycle time too.
Yeah.
One way to do is to say you're going to do, you know, the same human does two parallel tasks with the two robots.
Yes.
Another way is to say, just like your allocation right now, add a third row and allocate some of the tasks to another robot. Right?
Yes.
Just arbitrarily expand number of robots, but of course,
Yep.
then you're going to run into issues with the utility function not wanting to make assignments to the robots because the tasks are better performed by a human. So
Exactly. Yeah.
there's a trade-off there, right?
Yes. Yes. Also, you need to consider the cost. The economic return, if we add another robot, we will also add another overhead cost, and this makes maybe under consideration. But I agree with you highly. So there are different options here to try to improve the system productivity while still making the worker safe.
Right, right. So another question we had was about the task models. So, you know, the first study you sort of had this HTA, and I'm guessing that that's something that's built manually, right? The hierarchy.
Manually, yes.
Yeah. That could come from a database if the product, you know, is identified, I guess.
Exactly, yes.
And then I wanted to ask, as a follow-up, in your third study where you're trying to recognize the task, is it possible to also try to construct the HTA rather than try to recognize the tasks? Do you know what I mean?
Construct the HTA. Do you mean try to automate this process? Use the AI algorithm to run this type of HTA?
Yeah. So like use the learning to do discovery, right? Like the task discovery, rather than just pure, am I correct or not? And I'm asking that question as a lead up to another follow-up question, because if you are able to, let's say you're trying to recognize a task model, maybe the high level things are easier to recognize, right? Like you had those 5 things to do.
Yes.
I recognize those, but beyond those, I'm not so sure. Even if you can identify the top 5, you might still be able to take some action, you know, without having to recognize the entire task. Right? I'm wondering if this sort of like incremental approaches, blending learning with, you know, these more traditional task modeling techniques that could get you some other options rather than just purely looking at accuracy of recognition.
I think so. I think that is a very interesting aspect to explore. And in terms of generating the task analysis using HTA, so up until now, right now, we have a big assumption is the status of end of life products are similar, which means each module has some value to be recycled. So that means, you know, for each similar product, we can go to that level of subtasks. But if this is very likely that in reality, some of the status of those products are not identical or not similar, you know, maybe for one product, so the screen has crashed or, you know, has some other unreversible status, we can only recycle one part out of it. So which means for some modules, we do not need to go to that and finish all subtasks. Right. So in that case, I think we can, you know, try to leverage the capability of maybe some learning tools as well as, but the humans still need to be keeping the loop to make the big decision and the overall decision. So, but I think that is the interesting question to explore. I may need to discuss this with my team. So I'm not an expert on this.
Yeah. there is another question. So I have one more burning question. Since people are not asking, I'll ask it.
Sure.
I wonder if sort of a human in the loop approach might also give you some mileage. You know, where, you know, instead of the system looking through the entire space of recognition,
Yeah.
the human just points at something and that just constrains the space so much that, you know, like somehow you're able to better, you know, just look at this, or I realize the screen is cracked, just look at that kind of thing. Like, what are places where you can bring the human into the recognition that would make
Exactly.
recognition
Yeah.
much easier?
Yes, I agree, Hardy. So yeah, I think this is maybe the one of the directions, right? By leveraging the strengths of different sides. So human, maybe some very simple human impulse can significantly shrinking the search base of for the algorithms, right? For example, one particular application I can think of is maybe not for this desktop or remanufacturing, for some other electronic products, which are the plastics are a primary concern for recycle, and humans can identify the category of plastics much easier than some of the machine sensors. And these, maybe there's a plate here or a code for humans to identify. But even without those codes, with those QR codes, maybe this is pretty easy for a computer vision problem to identify the model, and you know what type of plastics and what type of techniques should be used. But if without those the codes, if those labels are gone, so then maybe human a better candidate for running some simple analysis, identify the potential make of the product, and identify the appropriate handling strategy.
Right, right. Great. Mike, do you have any questions? If not, I have one more question I can ask, but I wanted to see if I'm missing any of yours.
Go for it if you have a good one.
Okay, so you know, in our work, for example, we work on assembly,
Yeah.
and we're thinking about task models in terms of putting things together.
Mhm.
I wondered if you can learn things from assembly models to do disassembly. And maybe, you know, if you look at sufficient number of assembly models, and there might be more, that could tell you some principles that you can extract that could apply to many disassembly kind of tasks. Any thoughts?
Definitely. I think so. I think so. At least part of the operations can be, you know, but some of the process can be learned. They are simply reversible operations, but there are some tasks that are non-reversible. Okay, so I can give you an example that which actually illustrate the complexity of remanufacturing or recycling. So actually, my MacBook, the battery died last month or 2 months ago, and we had to manually replace the battery, and that was much harder than we expected. You know, the battery was attached, and you know, use glues attached to the aluminum frame.
Yeah, I was thinking about gluing, welding. These are not.
Yes, so this is super sturdy. We use the 3 men to pull the battery now. This task looks easy, but it's impossible to be handled by current robotics technology. Yeah.
Great. Yeah, thank you. This is very interesting. So sorry, I had so many questions. I don't see any other questions. I think we can wrap it up. Thank you very much, Boyi, for the interesting talk and answering all of our questions. And to close things up, I'll invite everyone to continue attending our talks. Next semester, we'll continue with the first Wednesday of February with our next speaker. Thank you, Boyi, again, and thank you everyone for attending.
Thank you.